Hello everyone and welcome to today's lecture. Today I'm going to be introducing the concept of sequences, which will then naturally kind of progress into the topic of series, which will be the next lecture video. But for today, we want to kind of just get a hold and a grasp of what exactly a sequence is and why these objects come up very, very often in not just in theoretical mathematics, but in applied mathematics as well. Exactly, put an infinite sequence is a list of infinitely many real numbers and we can have sequences of other such numbers, complex numbers. We can even have sequences of more complicated mathematical objects, but typically this is how we see a sequence written. So A0, A1, A2, and so on and so forth, all the way up to some AN, all the way up to infinity. We sometimes abbreviate this as AK from K, or for K from 1 to infinity, or sometimes just AN to denote this list of values. So in this class, we're really just going to be focusing on sequences of real numbers, but it's important that you realize there are other more advanced type of sequences that come up in more advanced applied mathematics and theoretical mathematics courses. I also want to make a note here that a finite sequence say we have a finite sequence or a sequence of values, just A1 up to AN, can also be described as an infinite sequence that has zeros on its tail, or the end of the sequence. And one of the things that we're very interested in mathematics and in applied mathematics, I'd say more in applied mathematics, is the limit of such a sequence. And what I'm going to do is provide you a very neat, motivating example that's a very applicable real-world example. And this actually comes from one of my favorite calculus books by Carl Lutzer and Tim Goodwill. Their Introduction to Calculus book. It's a very, very good book, and this example is right from the first chapter on infinite sequences. So for this example, what I want you to think of is what happens to the amount of, say, a given medication in your bloodstream after you have administered the medication. So say Tylenol or some other medication. There's many different types of medications for many different types of illnesses, but the idea is that consider that decay of concentration of some medication in the bloodstream. And this can be modeled by the most basic decay differential equation, the differential equation of exponential decay. And you may have seen this in your Calculus 2 course, or you definitely will see this in your differential equations course if you end up taking this course. But the differential equation that governs this is that the rate of change of the medication in the bloodstream is negative R times the current amount of medication in the bloodstream. This is the standard equation of exponential decay. And it's relatively straightforward to show that the solution to this differential equation is that the concentration of the medication in the bloodstream, A of t, is equal to A naught, the initial concentration, times e to the negative r times t. So r is the decay rate, t is time, A of t is the concentration at time t, and A naught here is the initial amount of medication administered. So this is an image showing what the concentration in the bloodstream would look like over time, and how it would decay over time for an initial dosage of, say, 650 milligrams, with a decay rate that gives a half-life of every 8 hours. So we're assuming here that the half-life is every 8 hours, and that 650 milligrams is the initial dosage. You see that it decays relatively fast, and over by about, say, 50 hours, the amount in the bloodstream is essentially zero. But this is not typically how medication is described or prescribed. Typically, we have to take a dosage on a regular basis repeatedly. So say, we'll take a 650 milligram dosage every 8 hours. And so every 8 hours here, we should actually expect this to this process to repeat itself. I'm going to show now what happens when this is the case. So what I mean by this is that after 8 hours, when we get to right here, to this point right here, the concentration decays down to a certain point. And instead of continuing to decay, we're going to say we're going to have another dosage of 650 milligrams. So our value of concentration should jump up by 650 here, and the decay process will repeat again. So if we continue this process, and you'll see what happens. We actually get two very important sequences here. So this is after 10 dosage cycles. Basically, we take our initial dose, the medication decays, we take another dose, the medication decays again, we take another dose, the medication decays, another dose, so on and so forth. And so what we have here are two very important sequences associated with this process. It's a sequence of high values, the upper y coordinates of each one of these points, and a sequence of low values. Right? You can ask, well, why are these two sequences of values important? Specifically, why is the limit of these two sequences important? And there's a very practical reason as to why these are important. I'll put two lines here. Well, every medication is going to have a level above which it's unsafe, a concentration at which above that level it's unsafe. Every medication is also going to have a lower bound or a lower level where below that level it's not effective, it's ineffective. So essentially, the limit of both of these sequences is very important, because we want to make sure that the upper level sequence has a limit that's below the danger level for whatever the medication is. For instance, if the safety level is right here, this is a very bad dosage regimen for our medication because we're getting above the level where it's safe to administer that concentration of medication at a given time. So we want to make sure that the limit of this sequence, or what the sequence is tending to, and the limit as n goes to infinity, is below this lethal level, but also above the effective level, so that the medication is actually doing its job. Right? We don't want something like this. We want it to be in between these two levels. So one of the things now that we want to do is kind of get a hold of what this upper bound sequence is. How can we describe it? And the way that we can describe this directly is by just writing that the kth term in this sequence is equal to 1/2 the k minus first term in this sequence plus the value of the dose being administered at that time. And this is for k equals 1, 2, and however many dosages that we're going to do. So this is one way of writing down this sequence, and this is actually what's called the recursive definition of this sequence, because the kth term in the sequence depends on the k minus first term in the sequence. Right? The initial dosage is A0, and then A1 is going to be 1/2 A0 plus A0. A2 is going to be 1/2 A1 plus A0, and so on and so forth. So this is a great example for me to kind of lead into the definition of a recursive sequence, or a recursively defined sequence. So we say that a sequence is defined recursively, or it's a recursive sequence, if it is described, say if it is a function of one or more previous values. And specifically, instead of it, I'll say the kth term. So AK is a function of one or more previous values. Specifically, we say that AK is equal to some function g of AK minus 1, where the starting point of the sequence is some fixed value. And I want to really emphasize here that this g, this function g, could also be a multivariable function. It could depend on ak minus 1, ak minus 2, and so on and so forth. If it depends on two previous terms, then we have to fix two initial starting values, or they're sometimes called seed values for the sequence. But the idea then is that if you were to write this sequence out, you would have that A1, A2, A3, and so on and so forth in the sequence. The same thing as g of A0. A2 is going to be the function g of A1. Right, this value is A1. A3 is going to be g of A2, where this value is A2, and so on and so forth. So what we can say is that the limit of such a sequence exists if we can solve the following equation. L is equal to g of L. And we're really only going to be looking at continuous functions, g. So one of our assumptions here is that g of x is continuous. And the motivation here is very clear. I think the idea here is that so this equation is coming directly from the process of taking a limit of the sequence, and if this limit exists, then this is going to be equal to L, but this is the same thing as taking the limit as k goes to infinity of g of ak minus 1. And so the idea here is that g is going to have the properties, some nice properties, specifically if g is continuous. We can say that this is going to be the same thing as g of the limit as k goes to infinity of ak minus 1. And this limit as k goes to infinity of ak minus 1 is the same thing as the limit of the sequence. It's going to the same place as k goes to infinity. So this is going to be g of L. And it's important that you realize that for a given problem, g is very often a nonlinear function. So we tend to have multiple different possible values for L, which are called limit points. And these limit points or limit values can be stable or unstable. And I'll get to that in a little bit when we talk about some examples, some good examples. So let's move back to the concentration example and just try and see if we can't solve our problem from before. The recursive sequence that we found was ak is equal to 1/2 ak minus 1 plus a naught, where our a naught was 650 milligrams. And what we're interested in is solving for the limit of ak as k goes to infinity. What is this equal to, if it even exists? So for this sequence, we have that our function, right here, this is our function g of ak minus 1. So the function g of x, the recursive definition of the sequence, is 1/2 x plus a naught. And we know then from that what I just showed that if this limit exists, we're going to have that AK is going to be going to this limit. So the limit of AK as k goes to infinity is going to be L. And the limit of AK minus 1 as k goes to infinity will also be L. So L should satisfy L equals 1/2 L plus A naught. We can directly solve for L here to get that L minus 1/2 L is going to be 1/2 L is equal to A naught, or L is equal to 2 times A naught. So in order to choose the correct initial concentration, or a fitting initial concentration, we have to choose A naught, right, so that this L is significantly less than the maximum lethal dose or harmful dose of this medicine. And this solves our problem. So specifically for this problem with the 650 initial dosage, we need to make sure that the lethal or the even dangerous dose is much, or the danger level is much higher than 1300 milligrams. So let's do one more example of a recursive sequence just to make sure that the concept is clear. Let's look at the sequence AK is equal to AK minus 1 cubed. And we'll fix A naught to be some value, and we'll kind of look at how the existence of a limit, depends on A naught. Because, depending on this function, it's going to be different in every different given case. The g function here that's defining this is the function g of x is equal to x cubed, because we're cubing the previous term in the sequence. And we know that from before, if the limit of AK exists, then the limit of the sequence AK is going to be L, and the limit of the sequence AK minus 1 is also going to be L. So the limit should satisfy L equals L cubed, which I can rewrite a little bit. I can rewrite this as L cubed minus L is equal to 0, or L times L squared minus 1 is equal to 0. And this algebraic equation has 3 separate solutions. As the solution L is equal to -1, the solution L is equal to 0, and the solution L is equal to 1. If I create, we'll just say a number line here, and I plot down each one of these values, the value -1 here, the value +1 here, and the value 0 here. I chose the colors here on purpose, red for -1 and 1, and blue for 0. What we're going to see when we go through and take a look at this sequence is that any value between -1 and 1, so any value in here, for a starting value of a naught is going to converge to 0. If we choose a naught to be 1 or negative 1, it's a naught is 1, the sequence is going to converge to 1. If a naught is negative 1, the sequence is going to converge to negative 1. And then for any value below negative 1, and for any value above positive 1, the sequence is going to either diverge to positive infinity or go to negative infinity for any starting value in this region. And what I want to do is show you this graphically so you can kind of see how we do have this difference between what's called a stable limit value and an unstable limit value. So negative 1 and 1 as starting points are both unstable, because if we move a little bit away, the sequence is going to move away from these values. But 0 is a stable limit value because moving a little bit away from it as a starting value will always result in us converging to 0 for the sequence. So let's take a look at this and see exactly what this means. So this is a visualization here of this sequence, various points in the sequence. For that's the first 20 points in the sequence, various values of a naught here. You see, if I start with a naught, any number greater than 1, even very, very close to 1. So if I come down to 1.01, which is pretty close to 1, you see that very quickly this sequence starts to diverge away from this point. The first couple points are relatively close to 1, but then by the first 5 terms of the sequence, we're starting to diverge very, very quickly away from 1. And sure enough, you can see this, that up to even the, this is the 0th term of the sequence, and 1, 2, 3, 4, 5, 6. Even the 6th term of the sequence is up to 1,000 already, from 11 to 1,000. So this is a very, very big very big jumping in this sequence very quickly. But then immediately when we go to 1, jump down to 1, the limit of this sequence is equal to 1. So this is one of the correct limits for this sequence. But then if I decrease just a little bit to 0.99, the limit of this sequence again changes, and it decreases very, very fast down to 0. And for all the values of the initial starting point for this sequence, going all the way down to 0, the limit of this sequence is still 0. All the way until we get to negative 0.99, where the moment we switch from negative 0.99 to negative 1, the limit of the sequence becomes negative 1. And if I go just a little bit lower, negative 1.01, we're again seeing this very quick divergence. So I think this is a very neat example, kind of illustrating the process of solving for limit points of recursive sequences, and showing the fact that sometimes you can have multiple different limiting values depending on the initial starting point for the sequence, and these can be stable or unstable. So moving on, I want to get to the other type of way of defining a sequence, and this is called the explicit way of defining a sequence. And this is if each term ak is given by a direct function of k. Or in other words, ak is equal to some function f of k. And I am specifically using f here as opposed to g from before because I don't want to confuse the two explicit and explicit and recursive definitions of a sequence. Now, given a sequence, sometimes the recursive definition is simpler, other times the explicit definition is simpler, but sometimes it's easier and nicer to use the explicit form of the sequence. Just go over a couple examples here to show you what I mean. So for the first example, I'll just say ak is equal to 1 plus k over k minus 1. So the terms in the sequence are when k is equal to 1, k plus 1 here. When k is equal to 1, this is going to be 1 plus 1 half. When k is equal to 2, this is going to be 1 plus 2 thirds. When k is equal to 3, this is going to be 1 plus 3 fourths, and so on and so forth. The limit of such a sequence can actually be directly evaluated in, I think, a slightly easier manner than the limit for recursive sequences. The limit of the sequence at k is the same thing as the limit as k goes to infinity of 1 plus k over k plus 1, which is going to be the same thing as 1 plus the limit as k goes to infinity of k over k plus 1. And what I'm going to do a little bit later on in the lecture is define what the limit actually is mathematically, what it means in terms of a mathematical definition. But I'm also going to write down the formal rules for limit calculation. And what's really nice is that all of these are very, very similar, if not exactly the same, to the limit rules for functions, which you learned hopefully in your Calculus 1 class. But the idea here is that we will be able to apply L'Hopital's rule. You'll notice that this is an indeterminate form, and we can actually directly apply L'Hopital's rule to this to get 1 plus this limit right here is going to be 1. So the limit of this sequence is in fact equal to 2. So I'll summarize these rules a little bit later on in the lecture. But what's really, really nice is that all of the familiar rules from our calculating limits for functions are going to directly extend to limits for sequences, which is very cool. So this is a good example of an explicitly defined sequence. I'll do one more, and I'll relate it to the previous example of recursive sequence that I went over. The sequence ak is equal to ak minus 1 cubed. Remember, this is the recursive form of this sequence. And this will show you how you can take a recursive form of a sequence and sometimes bring this into the explicit form for the sequence. And it just requires a little bit of investigation. You see, a1 here is going to be a0 cubed. a2 then is going to be a1 cubed, which is the same thing as ak minus 1, a0 cubed, which is in fact the same thing as a naught to the 3 times 3, or a naught to the 3 squared. If we do a 3, this is going to be a 2. This is going to be a 2 cubed, or a naught to the 3 squared cubed, which is going to result in a naught to the 3 cubed, or a naught to the 3 squared times 3, which is a naught to the 3 cubed. We'll do one more for good measure. This is going to be a naught, or a 4 is a 3 cubed, which is going to be a naught to the 3 cubed, which is going to be a naught to the 3 cubed times 3, or a naught to the 3 to the power 4. And hopefully you're seeing the general pattern here. We have that AK is going to be equal to a naught to the power 3 to the power k. Or if you want to put a parenthesis here, you can kind of surround the naught in a parenthesis just to be exact here. But this is the correct explicit form for this sequence, because it's giving you the exact value of the kth term in the sequence as a direct function of k. Basically, for a given starting position a naught, the kth term in the sequence is going to be that starting value a naught to the power 3 to the k. So it's a direct explicit function of k. So that's why we call it the explicit form of the sequence. So for a given sequence, sometimes the explicit form is easier to deal with, sometimes the implicit form is easier to deal with. It really depends on the example that you're looking at. So for the final part of the lecture, what I want to do is touch on some things that are going to be really important for us when investigating sequences. The first thing is that I want to rigorously define, write down the definition of what it means for the limit to exist. And so we say that the sequence AK converges to L. The notation for this is that the limit as k goes to infinity of AK is equal to L. So this happens if for every positive real value, no matter how small, there corresponds an integer. We'll call this n, such that the distance between the kth term of the sequence and the limit is less than epsilon whenever k is greater than this value n. If no such L exists, then we say the sequence diverges. So this is the mathematical way of exactly defining what it means for a sequence to converge. It's this definitive statement. And proving it in general is generally quite for complicated functions, it can be quite tricky. It's not too bad for relatively simple functions, but this can be a little bit tricky for more complicated functions. There are a number of really good examples in the book, but I just want to give you a graphical visualization of what it means for this definition, what this definition is saying. So let's take a given example sequence that appears to be converging. Right, it's getting closer and closer and closer to this limit value. So what this definition is saying is that for any epsilon, no matter, and I'm using S here as my epsilon, no matter how small I want to make that epsilon, there will always be a point in the domain of the sequence. So there'll always be a point in the sequence. In this case, this is our n, our capital N in the definition. So this is the point right here in the sequence. But there'll always be a point such that all of the terms past that point are within that epsilon tube. So if we make epsilon a little bit smaller, in general, that point is going to stretch further and further out into the sequence, possibly. But eventually there'll be a point where all of the terms past that n, that capital N, remain inside that epsilon tube. So this is the exact correct mathematical definition of the limit and a nice visualization to accompany that. This can be contrasted with a different example of a sequence that does not converge, so a sequence that diverges. So if we take a look at this sequence right here, which is L plus cosine of x times pi over 2 times 1 plus 1 over x, right, this sequence does not diverge because for any value of epsilon we choose, no matter how small we choose epsilon, there will never be a point which traps values of the sequence. No matter how large of an n we choose, there'll never be a point which traps all terms after this point in the sequence. So this sequence limit does not exist and does not converge. It diverges. We have two special types of divergence that we could have for some sequence, which are very important sometimes when we're looking at infinite limits, which are diverge to positive infinity sometimes, and divergence to negative infinity, which are defined very similar to how we define them for when a function diverges to positive infinity or negative infinity. So that example that I just showed was the just a general, how you should generally think of divergence. However, for many different examples, we can have this special type of divergence, which is more meaningful. So I'll put special divergence right here. A sequence AK diverges to infinity if for every upper bound m there exists an integer n such that for all k greater than n, the kth term of the sequence is greater than m. Basically saying that there's no upper bound for the sequence. And we said that this is the case where the limit as k goes to infinity of ak is equal to positive infinity. Another notation for this is ak arrow positive infinity. By the way, if you have convergence, another notation, a common notation for convergence, is to say that ak arrow L, which just means that the sequence converges to the limit of L. And we have a very similar statement for divergence to negative infinity. So similar, in fact, that I'm just going to copy this over and change a few things here so that I don't have to rewrite it. The sequence diverges to negative infinity if for every number m, I'll choose lowercase m for a lower bound. There exists an integer n such that for all k greater than n, the sequence ak is less than lowercase m. And if this is the case, then say that the limit as k goes to infinity of ak is equal to negative infinity, or ak arrow negative infinity. So these definitions are very, very similar to what it means for a function to go to positive or negative infinity. So for the final part of this lecture, I want to just kind of cover some of the basic rules that we have for convergent sequences. These are rules that are very similar to the rules for functions from Calculus 1 and are very useful in calculating limits, helping us along the way. All of these rules can be proven using the definition from before for convergent sequences with that this epsilon n definition right here. I'm not going to go over the proofs because they're not super important for this course. They are interesting, but really we just want to learn how to use these rules because it's going to be important for us when we get to series. So for the basic rules here, we're going to assume for all of these that the limit of the sequence ak is equal to a, and the limit of a sequence bk is equal to b as k goes to infinity. And so we're assuming that we have two convergent sequences. Our first main rule is that it's called the sum rule. The limit of the sum of sequence ak with sequence bk will always be the same thing as the sum of the limits. So the limit of ak plus the limit of bk, which will just be a plus b if capital A and capital B are the limits of the two original sequences. We also have a constant multiple rule, which says that the limit of a constant times ak will be the constant times that limit, or c times a. We have a difference rule, which is pretty much the same thing as the sum rule, just with a negative sign. The limit of ak minus bk will always be the limit of ak minus the limit of bk, which is just a minus b. We have a product limit law, which says that the limit of a sequence ak times bk will be the same thing as the limit of ak times the limit of bk, or a times b. And lastly, we have a quotient limit law, and this only holds when the limit of the denominator is 0, so the b's are non-zero. But this is that the limit of ak over bk will be the limit of ak over the limit of bk, which is a divided by b. So all of these should be familiar to you and similar to the limit laws for functions, almost exactly the same, really, as the limit laws for functions, which should make this process of calculating limits of sequences, I think, very similar to when you learned how to compute limits of functions back in Calculus 1. So in addition to these more basic rules, we also have a few slightly more advanced theorems that will help us in more complicated situations. The first theorem is called the Squeeze Theorem, or Sandwich Theorem, depending on what book you're using or who you took your Calculus 1 class with. But this basically says that if an, bn, and cn are sequences, that satisfy two conditions. The first one is that for any n, an is less than or equal to bn is less than or equal to cn. And the second condition, so this is true, and then also we have that the limit as n goes to infinity of an is equal to the limit as n goes to infinity of cn. These two values are the same. Then this theorem is telling us that the limit as n goes to infinity of bn must in fact be equal to L, the same limit as an and cn. And this is called the squeeze or sandwich theorem because basically this is the reason this is true is we're basically having this bn be sandwiched or squeezed between two separate sequences that are both converging to the same value. So if bn looks like this, maybe you have a sequence up top above it, which is the cn sequence, and a sequence below it, which is the cn sequence, the an sequence. If these two things are going to the same limit, then it forces bn to go to that limit as well. A very common example of this theorem is the sequence. We have the sequence bn is sine of n over n. We know that sine of n over n will always be bounded above by 1 over n and below by negative 1 over n. And we know that the limit as n goes to infinity of negative 1 over n is the same thing as the limit as n goes to infinity of positive 1 over n. They're both equal to 0. So therefore, by the squeeze theorem, the limit as n goes to infinity of sine of n over n must also be equal to 0. This is an alternative proof method for this function than using L'Hopital's rule. You could also go through and use L'Hopital's rule for this. You'll get the exact same answer, that it equals 0. But the squeeze theorem is an alternative method of proving this, and it's very useful under the right circumstances. On the subject of L'Hopital's rule, one of the very nice results that we have is that if a sequence is defined by a function, which allows for use of L'Hopital's rule. So, for instance, we have a function of f of x such that for x greater than or equal to some value n naught in the sequence, an is equal to f of n for all n greater than n naught, greater than or equal to, then the limit as n goes to infinity of an equals L whenever the limit as n goes to infinity of, or as x goes to infinity of f of x is equal to L. So what this is saying is essentially, and I shouldn't just say L'Hopital's rule, this is just a general limit rule for sequences. L'Hopital's rule is a good example of how we can use this theorem. But the idea that this is saying is essentially that, so if we have a sequence an, so for example, just do an example of this, an is equal to n plus 1 over n, we know that this is very, very similar to the function f of x is equal to x plus 1 over n. It's actually coming from this function right here, x plus 1 over x, sorry. So what this is saying is that as long as the limit as x goes to infinity of x plus 1 over x exists, which it sure enough does, right? If you use L'Hopital's rule here, you'll get that this limit is equal to 1. The limit of the corresponding sequence that's related to this function, n plus 1 over n, also has the same limit. So this is where this is useful. Basically, it's saying that we can use L'Hopital's rule for sequences, and really any other limit rules that we have, we can use for sequences, which is really, really, really nice, and allows us to extend pretty much all of the limit laws. One final very important theorem that's a little bit more advanced is related to the previous theorem, and this is called the continuous function theorem. And this basically is saying that if an is a sequence, and an converges to some limit L, and if f is a continuous function, then f of an, the function value on the sequence, converges to f of L. So for example, using the result of the previous example, if an is the square root of n plus 1 over n, since the sequence n plus 1 over n converges to 1, then square root of n plus 1 over n, our an sequence, has to converge to the square root of 1 or 1 as well, because the square root function is a continuous function. So the final thing that I want to leave you with is a sort of homework assignment. It won't be collected, but it's, I think, a good practice to get in the habit of. I want you to go through and prove, right, the following 6 limits using the limit laws and the things that I talked about at the very end of this lecture. So this is limit 1 right here. Is the limit as n goes to infinity of the natural log of n over n is 0. The limit as n goes to infinity of the nth root of n is 1. The limit as n goes to infinity of x to the 1 over n is 1 for any positive x. The limit as n goes to infinity of x to the n equals 0 if the absolute value of x is less than 1. The limit as n goes to infinity of 1 plus x over n to the n is equal to e to the x for any value of x. And the final one, number 6 here, the limit as n goes to infinity of x to the n over n factorial is equal to 0 for any value of x. I think that using your knowledge of L'Hopital's rule and some of the other limit laws that we went over, the 1 through 5 shouldn't be too difficult, and 6 isn't that bad either. You just want to remember that the factorial function, you might not have seen this function before. It's a function on the natural numbers that's defined in the following way. 0 factorial is 1, and n factorial for any number greater than 0 is just going to be the multiplication of all natural numbers up to that number, including the number as well. So these limits are going to be really, really important as we move along in the course and start getting into series. So you really want to kind of use this time to practice these limits so you can kind of know the limits and also see why they are the way they are. But this is a really, really good practice and because we're going to be using these limits a lot as we go forward. But thank you very much for tuning into the lecture today. I hope you had a great day and that you learned something.